Good afternoon. Last class I introduced a new framework for understanding the moving parts of the world. As I said when we started our discussion about energy, there is just one universe, hence the name universe. There is just one universe of moving bodies. And Newton's laws very completely describe that universe. If I want to know why an apple falls out of a tree or why the moon's going around the earth, Newton's laws give me a very accurate and descriptive picture of that. But we've developed a couple other frameworks or lenses for looking at the world that are sometimes much more helpful. So we saw a lot of situations involving energy where I can understand what's going on in a certain situation a lot easier, a lot more simply sometimes, if I'm not trying to figure out the forces and accelerations. Instead of looking at forces and accelerations, if I'm just looking at the energy of the system. So I'm looking at, does it have some sort of potential energy? Does that get converted into kinetic? Does that get dissipated as heat or something like that? That, for a lot of situations, is a much easier way to understand what's going on. Last class, we started talking about our third and final framework or lens for looking at moving stuff in the world, and that's momentum. The main utility of momentum and energy comes from the fact that they are often conserved. And so if I'm careful about defining my system and careful about measuring whether work is done or there's an impulse being done, the conservation of energy or the conservation of momentum is one of the things that really helps me understand a situation. Two types of situations in particular we talked about last class, I just want to mention again today. Two types of situations in particular that lend themselves to a momentum framework, and that's explosions and collisions. And so when I have a multi-body system, which we haven't talked much about this semester, when I have a multi-body system, when I have two things collide, two or more things colliding, or two or more things exploding or pushing off one another, momentum is a great framework to understand that. And by the way, I told myself I was going to start class with this, but I already forgot. Today's our 13th class. I haven't said this in 12 classes. Bless you. I haven't said this in 12 classes. I'll try to only say it every 12 classes or so. I can't tell you to not sit and just be on Reddit the whole class or showing your friends on Facebook. But I will say, having gone through 20 semesters of UVA, once I bought my laptop, my grades went down, and my enjoyment of class went down with my laptop. And so it took me a couple semesters to finally learn how to use technology appropriately in a class. And so they're a distraction. It can be a distraction to you. It can be a distraction to your neighbor. So if you have technology with you, please use it appropriately. That's my last plea for another 12 or 13 classes. Okay. Anyway, back to momentum. So we're going to use momentum for a couple types of situations, primarily collisions and explosions. So when I have two things colliding, let's see if I have two elastic balls. When I have two things colliding, let's say I've got two balls that are going to run into each other, and nothing in this universe is entirely rigid, and so they're going to deform a little bit. That deformation, if I've got like a tennis ball and a racquetball, that one's not bad. There. Okay. If I've got a tennis ball and a racquetball, that deformation is hopefully elastic. And if I have an elastic collision, they're going to return to the original shape, and I have actually not lost any energy. So actually, they've gone from kinetic energy into spring potential energy, and then I go back into kinetic energy. That's the definition of an elastic collision. An elastic collision is one in which I don't lose any energy. So energy actually can be a good framework for understanding elastic collisions. Most collisions are not elastic. If you think of just about any two things running into each other, you're usually not going to get all your energy back. Even this nice, supposedly bouncy ball, I have to kind of throw it down if I want to get my energy back. And then there's this one that doesn't even come close. And so most collisions are not elastic. Think about two cars not even slamming into each other, just two cars bumping into each other. if there's any sound, if there's any friction, if there's any heat, if there's any bending or deformation that's permanent, I've lost energy there. And energy becomes a very difficult way to understand collisions because they're usually not elastic. There's usually going to be energy losses, and those energy losses are very tough to calculate. And so if it was just like a box sliding due to friction, I can calculate that energy loss. But if it's two cars running into each other and the fenders bend and the hood pops off, that's much more difficult to understand from an energy standpoint. Similarly, think about some sort of explosion. And the easiest type of explosion I can think of, and again, this is you wouldn't normally think of this as an explosion, but I don't know, two people standing next to each other stationary, and then one guy just shoves the other one. That's sort of like an explosion. There was something sitting there with no energy and no momentum, and all of a sudden there's kinetic energy everywhere. So that, again, becomes a difficult situation to understand if I'm thinking about energy, because a bomb or just two guys standing there stationary, there's no energy there. There's no kinetic energy. So I'm starting looking at something stationary. And all of a sudden there's stuff moving. Where did all that energy come from? Well, if it's just a guy shoving his friend, that came from breakfast, and it's really hard to calculate how much breakfast you used in that push. Or in the case of some sort of bomb, there was either chemical potential or pressure potential, something that caused pieces to go flying. So if I try to understand what's going on in terms of energy, that's very difficult. But the cool thing about momentum is, let's see, I'll pull the equation up. What we saw last class is that that bottom equation says if two things push on each other equal and opposite for the same amount of time, they're going to equally trade momentum. And so if I have some object sitting stationary in the front of the room right now, I don't know, my laptop. Hopefully my laptop will not explode. iPhones these days, you never know. But so my laptop is sitting there. It has no momentum. It's no velocity. Momentum is just mass times velocity. It's got no velocity, therefore it's no momentum. If it were to explode into 7 pieces right now, the sums of those 7 pieces, the sums of their momentum would sum to 0. And so that makes it easy for me to understand what's going on. And obviously a much more simple situation would be my laptop splits in half and goes flying away in 2 pieces. The total momentum of those 2 pieces would have to be 0. Because the way they got from sitting there to flying apart was they pushed on each other. And they pushed on each other for the same F, equal and opposite, for the same amount of time. And so they just traded momentum. And so momentum becomes a really good way to understand explosions, collisions, situations like that. Okay. Any questions? One of my favorite ways that we use momentum, and again, this could be considered an explosion. And when I think of explosion, I just think of any two things flying apart. One of my favorite uses of the concept of momentum is in rockets. I like rockets. I think I had rockets on my pajamas until recently. So let's start with an eye clicker about rockets. Here's the eye clicker. Question for now, maybe of the day. Elon Musk's company SpaceX launches their next rocket. There's a picture, I think, of a SpaceX rocket blasting off. It's headed into orbit. It's headed out of Earth's atmosphere. What's it pushing off of? A, launch pad, B, the air, C, exhaust, D, inertia. Okay, 10 more seconds. And we're done. Okay. Nice. sure I want to give it away. Okay, so yeah, I'll explain it. So there's lots of ways that we humans have figured out to get around without touching the ground. Rockets are one of them, but rockets are particular for one reason, and rockets are the only way we've come up with so far to fly around in space. So one of the nice things about rockets, a propeller plane or a jet engine wouldn't work in space. A lot of the ways we get around here close to the surface of the Earth wouldn't work in space. In space, where you have no air, nothing else, here's how rockets work. Here's how a rocket works. Here's how a rocket works near the surface, but particularly useful when you're flying around and you're just in the emptiness of outer space. You got your rocket, maybe some people in there, and it's a bunch of fuel, and you ignite that fuel, and what you do is you organize that fuel and you direct that fuel. So in the combustion of the fuel, you've got a bunch of molecules that, well, usually in combustion you increase the number of molecules, so that's your first increase. And you usually go from a liquid or a solid into a gas. And I think we all know from some level of chemistry that when you go from a liquid or solid to a gas, you've got a much bigger volume. So all of a sudden I'm carrying with me my fuel. My fuel is some sort of rocket fuel, solid or liquid. And all of a sudden I convince that, usually through combustion, to expand in volume a lot. You've combusted, so you've got more molecules usually than you started with, and you're a gas. And then that rapid expansion, I can get a nozzle and I can shoot that out of the back of my rocket ship. And here's actually what's happening. Just like if I were standing on ice skates on a frozen lake and I had no friction and I wanted to go somewhere, one way I could do that is like take one of my shoes off and throw it, and I would go this way. So the conservation of momentum dictates that if something goes that way, something goes this way. We saw that last class with when you shoot a shotgun, something goes fast that way, something has to go that way, or a cannon. And so if I was standing on a frictionless surface and I threw something this way, I would go this way. Well, if you could have a huge, huge, huge million-pound rocket, and it could actually launch off the launch pad just by throwing out air molecules or exhaust molecules. So C, the answer is C. What it's pushing off of is exhaust molecules. And the launch pad is nice, but think about when the rocket is a mile up. It still can't be pushing on the launch pad. And air is nice. Air is a great thing to push off of. That's what most airplanes push off of. But if you're trying to get to space, you can only push on air for so long before you have nothing else to push off of. So rockets, the way rockets work is they literally throw tiny, tiny, tiny molecules out the back. When you think about a million-pound rocket versus a molecule, you wouldn't think that would get you much boost. One wouldn't. But they, first of all, shoot them very fast, so the V is high, and they just shoot a bazillion of them. And so when we're going to get in a little bit about how rockets work. You got to shoot a lot of them, and you got to shoot them very fast. But using that idea, using conservation of momentum, I can be a rocket, and I can just keep throwing stuff out the back of my rocket ship, and it keep accelerating, and I accelerate all day long. In fact, if we want to get to Mars or outside of our solar system or visit another star, chances are the way we're going to do that is by throwing just a small number of things out. So when Saturn V or the space shuttle takes off, I think they achieve more than 1 G of acceleration. It's a big blast off. But once we're trying to get very far, you can just throw out a molecule. You're out in space. There's nothing holding you back. You can just throw out molecules all day long and just keep accelerating and keep accelerating. So you can take a huge million-pound spaceship and accelerate to 1 mile an hour, and then a day later you're going 2 miles an hour, and a day later 3 miles an hour, just by shooting little electrons or some tiny thing out the back, and just accelerate and accelerate. All of a sudden, next thing you know, you're going 300 million miles. You can't go 300 million, that's speed light. But next thing you know, you're going 300,000 miles an hour, and all you've done is just throw molecules out the back. And so that's how rockets do their thing. I do want to talk a little bit more about how rockets work, because it's a crazy thing we humans do, this whole rocketry thing. So you probably know we put a guy on the moon. That was not a hoax. We actually did it. And we did it in the 60s before Google, before laptops, before the internet, before iPhones, yeah, it was amazing that we did that. So President Kennedy says, let's put a guy on the moon. NASA says, all right, we'll figure it out. And we put a guy on the moon. We put some guys on the moon. The Apollo program, I'm assuming most people know about this. The Apollo program was, the whole idea was shooting guys off and see if they can get them on the moon. And the Apollo guys, they flew on top of a Saturn V rocket. And so there's a picture of the Saturn V rocket. I don't know if you've ever seen one to scale. Or they have one, where did I see it? I think at the Kennedy Space Center down in Orlando. You definitely should stand next to a Saturn V someday in your life. It's crazy. They built this massive, massive, massive rocket there. It is bigger than Big Ben, way bigger than the Statue of Liberty, including the whole island that the Statue of Liberty is on. That's a big rocket. And here's my favorite thing about the Saturn V rocket. That spot there is where the guys live. Everything else is just a gas tank. And so here's the crazy, crazy endeavor. We actually convinced people to do this. Those guys that rode on top of those rockets were a lot of it insane. So what we said is let's just take a big can as taller than Big Ben, a big can, fill it with explosive, put little guys at the very, very, very top, and light it. It's completely nuts. And so one of the things about rockets, once you light one, you can't turn it off. You can't back off the gas pedal. It's just a big can of explosive. And so that little thing I circled, that's where the three guys would sit on top of a Big Ben worth of explosive, and we would blast them off the planet. Without nav system, without even like a cell phone, just with a page full of equations and a prayer, I guess is the way they did it. So here's what's nuts. If this is the Earth and we're blasting guys off, 1, 2, 3, 4, 5, 6, 7, 8. So to scale, I measured it. This is the moon right here to scale. So there's the Earth and everyone we know and everything we trust and love in our atmosphere. And here's the moon. And the way we're going to get there is by lighting an explosive and sitting on top of it and hoping we land on that and don't miss. Oh, and by the way, both of these things are moving. So we're launching off a moving planet and another satellite that's moving, and we're going to try to land on it. And then we're going to try to come back. And they did it. It's crazy. It's completely nuts that we've done that. And it's still one of my favorite accomplishments of our species. And there's a scale picture. You can barely see it. There's the Earth on the left. This is to scale. Hopefully you can see the moon on the right. I don't know if you can see it from where you are, but that's a scale picture. So that's what we were trying to traverse, is that big, scary gap. That's crazy. One of my favorite facts is you could actually fit all the other planets in that gap. You can fit Jupiter, Saturn, and all of them in that gap. It's a very large, empty space between us and our moon. That's not even between us and another planet. That's us and our little moon going around. So often it's drawn terribly, terribly not to scale. So that was the plan. Let's just put some guys on top of a can and light it and see if they get there. And brave or stupid, whatever you call them, they did. It was very dangerous. There were some lives lost in the process, as we probably know. But they did get that tiny little thing to orbit. They orbited the moon. The moon has enough gravity they could orbit. I feel so bad for the guy. So everyone knows it was Buzz Aldrin and Lance Armstrong actually set foot. And there had to be a guy in the, Mike Conrad maybe? I forget who the guy was. Gus Griffith? I don't remember. So some guy's job was just to stay in orbit. And so everyone knows the name of Neil Armstrong, but, oh, shoot. Mike Conrad, I hope it is. I don't know. I feel terrible that that's the case. So then they landed on the moon. They drove around. They brought a car with them at one of the missions, and then they drove around, and then they blasted off back, got in the orbiter, and then fell back to Earth. That was the only way we knew how to get back, and it's still a really good way to get back to Earth. Just get near enough that you fall in, and that was the plan, is we just fall in, and that's why the thing on top is just the shape of like a little bell, and it just comes through the atmosphere. It's going, I don't know, probably 20,000 miles an hour, hits all the gas, hits our atmosphere going 20,000 miles an hour. That's a lot of friction, creates a lot of heat. You see the glowing, you've probably seen those pictures, and the heat shield, and it glows, and they re-enter, then they deploy a parachute, and they fall into the ocean, and then we come get them. Crazy, crazy thing we did. It's so, but anyway, I love it. Okay. I have a version of that here in the classroom today that we're going to try to demonstrate. So this is my Saturn V rocket right here. And what I'm going to do is something fairly similar. I don't have a it's a liquid. It won't be liquid when I combust it. It'll be aerosol when I combust it. But, the whole hairspray thing, everyone I'm sure has done a hairspray in a lighter. So yeah, some people are in the good seats today. Michaela, you're right in the line of sight. Okay. So, pretty similar situation. So these guys on the Saturn V, they've just got a big can of gas and they light it. That's kind of what I'm going to do. I'm going to fill my container with a gas. So it'll be gas already. So that whole, the whole going from solid or liquid into gas thing, that won't be responsible for my change in volume. The change in volume will be, I'm going to combust the thing. So I'm going to combust the thing. I'm going to increase the temperature a lot. This is great, by the way. I'm so glad. I feel like the hairspray companies did all like 12-year-olds a favor. And if you look at the ingredients are fragrance and stuff, and then it's butane and propane. I feel like that's just a sneaky way to get butane and propane into your bathroom, because that's nuts that that's in here. And so those are two hydrocarbons, two combustible, flammable, volatile hydrocarbons. And so this thing is filled with dinosaurs, just like the same thing that drives my car around. This thing's filled with that stuff. Butane and propane are both fossil fuels. And so I've got fossil fuel in here. I'm going to light it. That's going to rapidly change in volume. They'll get a lot of heat. That's a big exothermic reaction. I'm going to get a lot of heat out of that, and a big change in volume. And I've got a little exhaust port. That's how rockets work. So I've got this chamber that I'm going to cause ignition to happen, and rather than just let the whole thing explode like a balloon, I'm going to direct that thing this way. So I'm going to have little molecules going that way. Conservation of momentum says something has to go that way. So that's the hope. I can pretend that there's some astronauts in there. They really badly want to see what's going on in the back of the room. So they're going to throw some gas molecules this way, and we should get some velocity that way. I don't know if it's going to make it all the way to the top. That's really far. Think about all the potential energy I have to gain, right? So it's going to get some kinetic energy, but it's also going up. So we'll see if we can get enough potential energy. See if we can get enough boost out of this thing. Let's try it. That one did not work. Not far enough. We're going to do that again. Okay, you heard it though. Okay. So I mean, that demonstrates the point, right? So we're going to do it again. We're definitely going to do that again. But you heard the gas leaving there's a little hole in this. You heard that going very fast. And it actually decreased. I got condensation in there. It decreased in volume enough, it actually crunched a little bit. Let's try that again. So this is just air. It's just air. I need to get some of that combusted fuel out of there. I need oxygen back in there. This is not a chemistry class, but you got to know we need oxygen if we want to combust, right? Let's try this one. It smells nice. Okay. So let's see. I am a Saturn V engineer. I just did my first test flight. I'm looking at the results saying, okay, that was nice. No one got hurt. We got a little altitude out of that. More fuel, I guess, is the... Try that. Let's try more fuel. That's interesting. Okay. That is weak. Okay. All right, we're going to try it one more time. Let's see. We're going to try that one more time, and then I have one that is sure to work. And while we're waiting for the one that's sure to work, I will be needing a volunteer for the next one, so be thinking ahead if you're going to volunteer. All right. That seems pretty good. All right. Saturn V engineer, thinking more fuel. All right, we're going to give this one more shot. It seems to work. Okay. Oh, I think I just realized what it was. This one's going to work. That was awesome. All right. All right. Pretty good. I would like to say, I think the two failures made that one better. I gotta remember that. That's way better. Fail a couple times first to build up this suspense. Okay. Everyone survived. Good. I think, yeah, okay, here's my next, this is my next, I'm not going to say trick because it's not a trick, this is physics, but this one's great, and I have another rocket. Here's my rocket here. It's a rocket car, and I know someone wants to volunteer to be my astronaut. So, yeah, all right, come on up. Yep. Oh, wait. Rebecca, let's do two. Yeah, let's do two. Not at the same time, but yeah, come on. All right, we have to do some sort of competition now that we have two astronauts. Let's do, okay, you're going to go, I think with the plane, I think that we come over here. So I think the competition will be who can give themselves just the right amount of blast that they get to the other side of the room. So you want to accelerate, and then it's going to slow down, right? When you're sitting on it, it's not going to roll for, well, that's pretty good. All right, the competition is to see who can get to the other side of the room without hurting themselves. Okay. All right, so go ahead and take a seat. And you can sit two ways. I think the scary way is to sit backwards, and you don't know what's going on. I'll spot. So you can sit backwards and you'll go that way, or you can sit front ways and just do this. But either way, you have to wear a helmet. Okay, I think that's the front. There you go. And you can also wear, actually, if you want to. It's pretty loud. You want to wear earmuffs? Yeah. All right. We're gonna be safe. Yeah, this does look much more legit. There it is. That looks very legit. Okay. So I am going to stand. I think you're aimed right. Okay. I think you're good. All right. I'm going to stand over here. So again, this is just conservation of momentum. This is similar to any type of rocket. This is a rocket cart where that's carbon dioxide. It's compressed carbon dioxide. Yeah, go ahead and just take a seat however you want. Okay, doing the scary way, that's fine. There we go. I'm going to arm your rocket cart, so whenever you squeeze this, you're going to start going. Not yet. And so what we have is compressed carbon dioxide. So this is, I don't know how many pounds, 150, 170, 180 pounds of person. that wants to start accelerating, that looks pretty straight. Good. So wants to start accelerating, 170 pounds worth of person is going to accelerate just by taking carbon dioxide gas, pretty light gas, and just throwing it this way, and they should accelerate this way. So what you're going to want to do, you're going to want to accelerate. You probably want to let off the gas around here so you have time to decelerate. Give it a shot. Go for it. There it is. Nice, nice. Okay. Do you want to rock it back?
Yes, it's that.
No, I mean, Rebecca wants to rock it back. Do you want to rock it? Yeah, you can rock it back. You went without the earmuffs?
Yeah.
Okay.
They wouldn't fit in the
How's your ears? Not too bad? Okay. Thank you very much. All right. All right. Doing the scary way, I'll spot. You look like you're aimed, right? Yep. I'll spot. Okay. So again, one more demonstration. Rebecca's going to shoot carbon dioxide that way, and as a result, conservation momentum. Right now, there is the Rebecca cart gas tank system has 0 momentum. Conservation momentum says that has to stay that way. So whatever momentum she has now, and it's 0, has to stay 0. So if you take something and go to the right, something has to go to the left. Ready? Give it a shot. Whoa. Okay. Nice. Okay. Good job. Thank you, guys. Thank you very much. Can you get it off? Okay. Yeah, it'd be a good way to get around grounds. Okay, thanks. And by the way, if you watch that, there might be a tendency to think the way she was propelled was by pushing off the wall. And I do want to make sure that's not that's not confused. Similarly, when you watch a rocket take off, there's a tendency to think, well, it's pushing off of the launch pad or something. There could be a big hole. In fact, often there is. There's often a big hole there because there's no point in just annihilating the launch pad. And so really what you're pushing off of is just the molecules themselves, the exhaust gas. And so even though you saw this big blast go up against the wall, really what she was pushing up against was the molecules themselves and just continuing to throw them out. Okay. Yes? Good question. The question was, can a rocket only be directed in a straight line? Yes. So there's ways around that. So when I throw, whatever direction I throw the molecules, I will go equal and opposite. So if I throw gas molecules this way, I will go this way. Now, if you watch most rockets take off, most rocket ships do have some steering, I guess. The exhaust gases can be directed. So if I have 2 exhaust or 3, I think Saturn V has 5, exhaust ports, I can angle them, and I can control it that way. Also, some things that use a similar type of propulsion have multiple ports, and you can just turn them on or off, or maybe control how much. And so if you have 2 exhaust ports, you can turn one more or turn the other. Turn one on more or open the port more, and you'll get more steering. NASA has some robots that fly around on the International Space Station, and the robots, the way they fly around, they have 12 little carbon dioxide jets, similar to that, much smaller than that, but similar to that, 12 jets, and they shoot out in different locations around. They're spherical. These little robots are little spherical robots, and they have 12 jets that shoot out. So if I want to go this way, I turn these 2 jets on. If I want to turn, I turn this jet on and the opposing jet, and I'll rotate. And I can get all kinds of complex motion out of these spherical robots just using more than one jet. Okay. Any other questions? Great. So we humans have figured out this whole rocket thing. It's still a crazy way, but pretty fun, way to get around. And that's primarily useful when you know you're going to be out of the atmosphere. And so we use rockets as, like I said, it's pretty much the only thing you can do when you don't have any air or ground or anything else to push off of. We've got 8 minutes left. I do want to talk about very quickly a couple other modes of travel, of air travel. And we'll start with another iClicker. 2 today. So I want to know how much the air in this room weighs. About as much as a hamburger. So you can imagine if you took all that air in the room, compressed it down, it might weigh about this much. Or maybe more, maybe like 5 pounds, like a heavy textbook. Maybe 100 pounds, like a person's amount of gas. Or 3,000 pounds, more than my car. Even split. It's nice. Okay, let's see. Take 10 more seconds. Okay. Pretty even split. If you said like B or C maybe, I think that's where I would have guessed. I actually did the math a little bit ago, and I had to double check my math a couple times. I thought, no way it's that much. If you took all the air, I mean, air weighs nothing, right? It's so light. It's just, you can hardly feel it. You took all the air in the room. It's very compressible, and you compressed it down to like the size of a basketball. You'd think that basketball would weigh, I don't know, pound, 5 pounds, something like that. There's actually, it was very rough math, it's actually about 3,000 pounds of air in this room right now. Bonkers. Bonkers if you think about it. So, but it's true. And so here's the reason I bring that up. As we humans have tried to figure out ways to get around, we need to go over oceans, and boats aren't fast enough yet, and we want to go. Yeah, planes are a pretty good way to get around. I think I enjoy air travel. I used to. It's such a pain now. But it's a good way to get around. But here's how planes work. They use air. And we often just negate air. We don't think of air as something significant. We don't think of that. How do you use air to get around? It's actually pretty substantial. There's 3,000 pounds of it in this room right now. So if I had 1 square meter, or if I had 1 cubic meter of air, so if I had just a cube of air in this big, right? Just a cubic meter of air, that would weigh 3 pounds. It's hard to believe, 3 pounds just in this, but you can like hold that much air. It's 3 pounds. So I think we need to swallow that, and we'll maybe do some more like just quick math so we believe it. But I think the reason we tend to not realize that this room is full of a gas that is actually pretty substantial. One, it gets out of the way pretty easily. And so if I had to swim through it all day long, I might be a little more respectful of it and realize, oh, that's a thing, if I had to really get through it. But it gets out of the way. But also, where I'm going with this is the idea of air pressure. Right now on my hand, I have some air pressure. But I also have some air pressure underneath my hand. And so since those cancel out, those pressures cancel out, so I don't really think about them all day long. But the pressure, let's think about this. So a cubic meter of air weighs about 3 pounds. So there's a cubic meter of air here, and here, and here. So this desk, I don't know, this desk is maybe 10 square meters. So the air on top of this desk, just this much air. We're not talking about the ceiling. So the air on top of this desk, 1 meter high, is about 30 pounds of air. There's 30 pounds pressing down on this just from this much air. But it doesn't end there. It goes to the ceiling, and on top of the ceiling there's some air, and it goes all the way to the top of the atmosphere. And every square meter of table is actually being pressed down under, like 1,000 pounds of force, something like that. It's a lot of pressure, every square meter. Your head right now, if you think about it, your head right now, you could take the cross-section of your head, has a cylinder of air from here to space sitting on it. And it's very, very heavy. It's very heavy. Oh, in fact, before we run out of time, we only have 4 minutes left. I do have one more demonstration of that. And then maybe next class we'll talk a little bit more about how airplanes use that. Don't pack up yet. I am going to talk more about space flight, but and air flight, or flying, I guess you'd call it. Let me try to demonstrate that. So right now in this room, every square inch has 15 pounds of air on it. That's hard to believe. Every square inch. So something a little bit bigger than a quarter has 15 pounds of air on it. Why so much? Because every square inch, just imagine a square inch on your hand or on your head or on a table. That square inch has a column of air up to space pressing down on it. I've mentioned before that the only reason we have an atmosphere is because the Earth, everything falls to Earth. Just like your car keys fall to Earth, so do gas molecules. So there's just a stack of gas molecules resting on this planet. And if you were to take any square inch column of them and take the mass, take the weight of them, you'd have about 15 pounds on every square inch. That's a lot. So the only reason we aren't all being crushed right now as we speak, as we sit here, is that that 15 pounds is canceled out by another 15 pounds. We all are in a pretty much pressure equilibrium. Same with this can right here. This can right here has a little bit of, tiny bit of water in the bottom, but it's mostly air. So there's air pressure on the inside. There's 15 pounds per square inch of pressure on the inside pushing out. There's also 15 pounds of air pressure on the outside pushing in. So the only reason this can is in a can shape right now is because those all cancel out. So what I'm going to try to do in the next minute or two is change that situation, and then we can talk more about how airplanes take advantage of this next class. But I'm going to change the situation by getting rid of the air in here. The way I'm going to get rid of the air in here is I'm going to boil the little bit of water that's in the bottom. So I'm going to add heat energy through, again, more hydrocarbons. Dinosaurs are useful. Then once the water boils, that water is going to turn into water vapor and displace the air in there. Then I'll have a can not full of air, but a can full of water vapor. Still, water vapor at atmospheric pressure and atmospheric pressure on the outside, still equilibrium. So I've got 15 pounds per square inch on the inside, 15 pounds per square inch on the outside. Then I'm going to put this in cold water. That will cause the water vapor to turn back into a liquid. I will rapidly decrease the volume. And here's what you're going to see. The pressure on the outside will do some damage. But I really want us to believe when it happens, nothing was sucking the can in. Often when you might imagine that the vacuum sucked it in. Nothing sucked it in. Vacuum isn't a thing. What happened was 15 pounds per square inch was pushing on the outside of the can. All right, we're running out of time. Let's try it. Should probably light that before it explodes. There we go. All right. Maybe should have started the boiling process before I started talking. While I was talking, I don't cook much, so I forgot that water doesn't boil immediately. But there's not much in there. I bet it starts boiling pretty quick. And so again, what we'll see, and I want us to really, this is what I want us to process, is what you're not seeing is something sucking the can in. You're going to watch air pressure on the outside just crush it. Just crush it from the air pressure. That might be boiling. We're going to do this maybe faster than it should be done just because we're running out of time. Is that boiling? Not quite. Let's see. All right, because I'm going to try it once because people are packing up, and then if it doesn't work, I'll do it again. I don't think that's boiling yet. Nope. All right, we'll just give it a try. It's not boiling yet. I'll give it a try real quick. Yeah. Well, You can kind of see it did it a little bit. It did a little bit. There was a little bit of pressure change. Yeah, there's a little bit of pressure change, but I'll do it one more time. So if you need to go, see you on Friday. I'll try one more time just for my own edification.